So hello everyone. So today we'll be discussing about the static compensator, that is STATCOM, one of the most important element of FACTS devices. Now, static synchronous compensator, that is STATCOM. Before this lecture, we already discussed about the synchronous compensator. A synchronous compensator is nothing but a synchronous machine which is operating at no load. So a synchronous motor without any mechanical load can be work as synchronous compensator. The synchronous compensator is a synchronous machine when overexcited or underexcited will able to produce or consume the reactive power. Now we know that the synchronous motor is a mechanical device, and to overcome the disadvantage of mechanical devices, we are using the static synchronous compensator, that is STATCOM. So basically, what is a STATCOM? So STATCOM is a shunt connected reactive power compensation device like the synchronous compensation, and it is capable of generating or absorbing reactive power. So its working is very much similar to synchronous compensator. The only difference between the static synchronous compensator, that is STATCOM, and synchronous compensator is that the synchronous compensator is a mechanical device and the static synchronous compensator is purely electronic or electrical device, and it is static in nature. Right? So a STATCOM is a shunt connected reactive power device which compensate the reactive power, and its output can be varied to control the specific parameter of the electrical power system. So a static synchronous compensator is a solid state switching converter, and it's capable of generating or absorbing independently the controllable real and the reactive power at its output terminal. So it is a solid state switching device. So it is basically consists of a voltage source converter. It consists of two it consists of thyristor bridge, and this bridge is connected with a energy source or energy storage device at its input terminal. Now, the STATCOM is considered is a voltage source converter, right? So it is basically a voltage source converter. Input of a DC voltage produces a set of three-phase AC output voltage, right? Each in phase with and coupled to the corresponding AC system voltage. So the STATCOM is a voltage source converter. It is connected with a DC source and it is producing a set of three-phase AC output voltage, and this output voltage is in phase with the grid AC system voltage, and it is connected through a small reactance. So here is the diagram of a STATCOM, right? Now remember all the diagrams. Here it is a utility voltage or ET. It is basically the transmission voltage, or you can say grid voltage. And here it is a STATCOM current, which is given by IQ. This is a magnetic coupling, a small reactance coupling, which is connecting the synchronous compensator, static synchronous compensator, that is a STATCOM, with the grid. This is a voltage source converter, and here it is a DC energy source. And in the most of cases, we will find that a capacitor bank is used as a DC energy sources. So it can be represented as a STATCOM with an internal voltage E STATCOM. It is connected through a reactance axis. A current I STATCOM is flowing, and it is provided to utility grid. Now remember, when the STATCOM voltage is greater than the transmission voltage, it supplies the reactive power, and whenever the STATCOM voltage is less than the utility voltage, it absorbs the reactive power. So in this case it will be a source, and in this case it will be a sink of reactive power. Now, what is the principle of operation of a STATCOM? Right? So we already discussed in the last figure, but here we'll be discussing. So STATCOM is a controlled reactive power source. It provides a desired reactive power generation and absorption entirely by means of electronic processing of the voltage and current waveform in a voltage source converter. So, first thing is clear that the STATCOM is a controlled reactive power source. It can be controlled by controlling the voltage source converter, right? We already discussed this. A single line diagram of STATCOM power circuit, which was shown in the previous slide in the figure A, and in which a voltage source converter is connected to a utility bus through a magnetic coupling. Now, STATCOM is seen an adjustable voltage source behind reactance, meaning that a capacitor bank and shunt reactor are not needed for reactive power generation and absorption. Right? In case of the thyristor control reactor and the thyristor switch capacitor, we needed a capacitor bank and a shunt reactor for the reactive power generation. But in case of a STATCOM, these all are not needed. So a STATCOM have a compact design, or you can say small footprint, as it's produce low noise and low magnetic impact. Right? So the exchange of reactive power between the converter and the AC system can be controlled by the controlling the amplitude of three-phase output voltage ES of the converter. We already discussed this concept in the previous slide. Now, if the amplitude of the output voltage is increased above the utility bus voltage ET, then a current flows through the reactance from the converter to the AC system, and the converter generates capacitive reactive power for the AC system. Right? And if the amplitude of the output voltage is decreased below the utility bus voltage, then the current flows from the AC system to the converter, and the converter absorbs inductive reactive power from the AC system. So it all depends upon the STATCOM output voltage, whether it is greater than the system or utility voltage, or it is low compared to the system or utility voltage. So if it is greater than the utility voltage, then it will produce the capacitive reactive power, and if it is low than the utility voltage, then it will consume the inductive reactive power. Now, this is third case. We can consider that if the output voltage is equal to the AC system voltage, then what will happen? So in this case, the reactive power exchange becomes zero, and the STATCOM comes into a floating state. So it will neither generating the reactive power nor consuming the reactive power. So it's in the floating state. Right? Now, adjusting the phase shift between the converter output voltage and the AC system voltage can control the real power exchange between the converter and the AC system. So by controlling the phase angle delta, we can control the real power exchange between the converter and the AC system. So the converter can also supply real power to the AC system from its DC energy source. If load angle delta is the phase shift, basically the phase shift between the output voltage of converter and the system or utility voltage is changed. Also, it can absorb real power. The converse of it's also true. It can absorb real power from AC system for the DC system if its voltage lags behind the AC system voltage. If the voltage of the converter is leading, then it will inject the real power into the utility system, and if its voltage, that is STATCOM voltage, is lagging behind the utility voltage, then it will consume the real power. So the STATCOM provides the desired reactive power by exchanging the instantaneous reactive power among the phases of the AC system. So, what is the mechanism behind how the converter internally generate or absorb the reactive power, right? So, it can be understood by the relationship between the output and input power of the converter, right? So, what is a converter work? How the converter works? The converter switches connect the DC input circuit directly to the AC output circuit, right? The net instantaneous power at the output terminal must always be equal to net instantaneous power at the DC input terminal. Now, assume that the converter is operated to supply reactive power output, right? So, our converter is supplying the reactive power output. In this case, the real power provided by DC source as input to the converter must be zero, right? Now, because the reactive power at the zero frequency, that is DC, is by definition zero, the DC source supplies no reactive power as input to the converter and thus clearly plays no part in the generation of reactive power output power by the converter. In other words, you can say that the converter simply interconnect the three output terminal so that the reactive output current can flow freely among them. Right? So, if the terminal of the AC system are regarded in this context, the converter establishes a circulating reactive power exchange among the phases. However, the real power that the converter exchange at its AC terminal with the AC system must of course be supplied to or absorbed from its DC terminal by the DC capacitor, right? So reactive power is generated internally by the action of converter switches. A DC capacitor must still be connected across the input terminal of the converter. So there is no role of DC capacitor in the generation of the reactive power. The reactive power is generated internally by the action of converter switches. That's why we are saying that for the reactive power at zero frequency by definition is zero. So DC source supplies no reactive power as input to the converter, right? So, what is the need of capacitor in the STATCOM? So, the primary need for the capacitor is to provide a circulating current path as well as voltage source. So, it will be, the capacitor will be acting as circulating current path provider. So, what is the magnitude of the capacitor so selected? So, the magnitude of the capacitor is chosen so that the DC voltage across its terminal remains fairly constant to prevent it from contributing to the ripples in the DC current. So the capacity of the capacitor bank must be that it prevents the contribution to the ripples current. So the voltage source converter output voltage is in the form of staircase wave into which a smooth sinusoidal current from the AC system is drawn, resulting in slight fluctuation in the output power of the converter. So the output voltage of the voltage source converter is staircase waveform, right? So this will produce a fluctuation in the output power of the converter due to the staircase output voltage, right? Now to not violate the instantaneous power equality constraint at its input and the output terminal, the converter must draw a fluctuating current from its DC source. As we know that, and it is previously discussed in this slide, that the instantaneous power must be remain constant. So the converter To keep this constant, the converter must draw a fluctuating current from DC source. Now, based on the converter configuration, it is possible to calculate minimum capacitance required to meet the system requirement. And what are the requirement? Requirement are ripple limits in the DC voltage and the rated reactive power support needed by AC system. So based on these two requirements, we can design or we can require a minimum capacitance to the STATCOM. The VSC has the same rated current capacity when it's operated with the capacitive or inductive reactive current. So the voltage source converter has the same rated current capacity, and a voltage source converter having a certain MV rating gives the STATCOM twice the dynamic range in MVAR. Right? So whatever the rating of voltage source converter, the STATCOM has twice the dynamic range in MVAR. A DC capacitor bank is used to support the controlled DC voltage needed for the operation of voltage source converter. Now the reactive power that is generated by the STATCOM is produced by means of power electronic equipment. And what is this? What and the power electronic equipment? That is voltage source converter. Now the voltage source converter that we are using in the STATCOM may be 2 level or 3 level, and it depends upon the requirement of output power and the voltage. So if a number of voltage source converter are combined in a multi-pulse connection to form the STATCOM. In the steady state, the voltage source converter operates with the fundamental frequency switching to minimize converter loss. But during the transient condition, which are caused by the line faults, the pulse width modulation mode is used for the switching of voltage source converter to prevent the fault current entering the VSC. To save the voltage source converter with the fault current, it can be operated in pulse width modulation, that is PWM mode. So in this way we can save, or we can the STATCOM is able to withstand the transient on the EC side without blocking. So without disconnecting the STATCOM from the system, it can be able to withstand this transient by using the PWM mode of operation. So here is the VI characteristics of STATCOM. Now we know that the STATCOM can supply both the capacitive and the inductive compensation, right? So it is able to supply both the capacitive reactive power and the inductive reactive power, and it is able to independently control its output current over the rated maximum capacitive or inductive range, right? So it can control the output current also. Now, the STATCOM can provide full capacitive reactive power at any system voltage, even as low as 0.15 per unit. So, it can provide the capacitive or reactive power at any system voltage. So, here is the diagram of the VI characteristic of the STATCOM, showing the inductive and the capacitive mode. On the left side we can find that there is the capacitive mode, and on the right side there is the inductive mode. Now the characteristic of STATCOM reveals another strength of this technology. That what the strength of this technology, that it is capable of yielding the full output of the capacitive generation almost independently of system voltage. That is the output capacitive generation does not depends upon the system voltage. It can provide, as we discussed in the previous slide, that it can provide the capacitive power generation as low as 0.15 per unit of the system voltage. So this is very much important in case or in situation where the STATCOM is needed to support the system voltage. And when we require to support the system voltage. This is during and after the fault where the voltage collapse would be a limiting factor, right? So figure the VI characteristic illustrate that the STATCOM has an increased transient rating in both the capacitive and the inductive operating region. The maximum attainable transient overcurrent in the capacitive region is determined by the maximum current turn off capability of the converter switches. Uh, the important thing is that in the inductive region, the converter switches are naturally commutated. So natural commutation is used in case of inductive region. Right? Thank you for listening. That's all for today, and in the next lecture we'll be discussing about the thyristor controlled series capacitor.